In mathematics, an equivalence relation is the relation that holds between two elements if and only if they are members of the same cell within a set that has been partitioned into cells such that every element of the set is a member of one and only one cell of the partition. The intersection of any two different cells is empty. The union of all the cells equals the original set. These cells are formally called equivalence classes. Notation. Although various notations are used throughout the literature to denote the two elements A and B of a set are equivalent with respect to an equivalence relation are, the most common are A to B, and AA permel B, which are used when A is the obvious relation being referenced, and variations of AB, AA permel are B, or AB otherwise. Definition: a given binary relation on a set X is said to be an equivalence relation if and only if it is reflexive, symmetric and transitive. Equivalently, for all A, B and C in X, A to A, if A to B then B to A, if A to B and B to C then A to C. X together with the relation is called a stoid. The equivalence class of A under, denoted, A, is defined as. Examples: simple example, let the set have the equivalence relation. The following sets are equivalence classes of this relation. The set of all equivalence classes for this relation is. Equivalence relations, the following are all equivalence relations, has the same birthday as on the set of all people. Is similar to on the set of all triangles. Is congruent to on the set of all triangles. Is parallel to on the set of lines in a plane from Euclidean geometry. Is congruent to, modulo n on the integers. Has the same image under a function on the elements of the domain of the function. Has the same absolute value on the set of real numbers, has the same cosine on the set of all angles. Relations that are not equivalences, the relation A permel n between real numbers is reflexive and transitive, but not symmetric. For example, 7 A permel 5 yen does not imply that 5 A permel 7 yen. It is, however, a partial order. The relation has a common factor greater than 1 with between natural numbers greater than 1, is reflexive and symmetric, but not transitive. The empty relation A on a non-empty set X is vacuously symmetric and transitive, but not reflexive. The relation is approximately equal to between real numbers, even if more precisely defined, is not an equivalence relation, because although reflexive and symmetric, it is not transitive, since multiple small changes can accumulate to become a big change. However, if the approximation is defined asymptotically, for example by saying that two functions f and g are approximately equal near some point if the limit of fg is 0 at that point, then this defines an equivalence relation. Connections to other relations: a partial order is a relation that is reflexive, antisymmetric, and transitive. A congruence relation is an equivalence relation whose domain X is also the underlying set for an algebraic structure, and which respects the additional structure. In general, congruence relations play the role of kernels of homomorphisms, and the quotient of a structure by a congruence relation can be formed. In many important cases congruence relations have an alternative representation as substructures of the structure on which they are defined. For example, the congruence relations on groups correspond to the normal subgroups. Equality is both an equivalence relation and a partial order. Equality is also the only relation on a set that is reflexive, symmetric and antisymmetric. A strict partial order is irreflexive, transitive, and asymmetric. A partial equivalence relation is transitive and symmetric. Transitive and symmetric imply reflexive if and only if for all or X, there exists a bar X such that A to B. A reflexive and symmetric relation is a dependency relation, if finite, and a tolerance relation if infinite. A preorder is reflexive and transitive. Well-definedness under an equivalence relation: if is an equivalence relation on X, and P, X, is a property of elements of X, such that whenever X to Y, P, X, is true if P, Y, is true, then the property P is said to be well-defined or a class invariant under the relation. A frequent particular case occurs when f is a function from X to another set Y. If x1 to x2 implies f, x1, equals f, x2, then f is said to be a morphism for, a class invariant under, or simply invariant under. This occurs, for example in the character theory of finite groups. The latter case with the function f can be expressed by a commutative triangle. See also invariant. Some authors use compatible with, or just respects instead of invariant under. More generally, a function may map equivalent arguments to equivalent values. Such a function is known as a morphism from A to B, equivalence class, quotient set, partition, let. Some definitions: equivalence class. A subset Y of X such that A to B holds for all A and B in Y, and never for A in Y and B outside Y, is called an equivalence class of X by. Let denote the equivalence class to which A belongs. All elements of X equivalent to each other are also elements of the same equivalence class. Quotient set. The set of all possible equivalence classes of X by, denoted, is the quotient set of X by. If X is a topological space, there is a natural way of transforming X/ into a topological space. See quotient space for the details. Projection. The projection of is the function defined by which maps elements of X into their respective equivalence classes by. Theorem on projections: let the function f, x a b be such that A to be a f, A, equals f, b. Then there is a unique function gar x/a b, such that f equals gi euro. If f is a surjection and A to be a f, A, equals f, b, then g is a bijection. Equivalence kernel. The equivalence kernel of a function f is the equivalence relation defined by. The equivalence kernel of an injection is the identity relation. Partition. A partition of X is a set P of non-empty subsets of X, such that every element of X is an element of a single element of P. Each element of P is a cell of the partition. Moreover, the elements of P are pairwise disjoint and their union is X, counting possible partitions. Let X be a finite set with n elements. Since every equivalence relation over X corresponds to a partition of X, and vice versa, the number of possible equivalence relations on X equals the number of distinct partitions of X, which is the nth Bell number Bn. Where the above is one of the ways to write the nth Bell number. Fundamental theorem of equivalence relations. A key result links equivalence relations and partitions. An equivalence relation on a set X partitions X. Conversely, corresponding to any partition of X, there exists an equivalence relation on X. In both cases, the cells of the partition of X are the equivalence classes of X by. Since each element of X belongs to a unique cell of any partition of X, and since each cell of the partition is identical to an equivalence class of X by, each element of X belongs to a unique equivalence class of X by. Thus there is a natural bijection from the set of all possible equivalence relations on X and the set of all partitions of X, comparing equivalence relations. If and A permil are two equivalence relations on the same set S, and A to B implies or permil B for all A, B or S, then A permil is said to be a coarser relation than, and is a finer relation than A permil. Equivalently, is finer than A permil if every equivalence class of is a subset of an equivalence class of A permil, and thus every equivalence class of A permil is a union of equivalence classes of. Is finer than A permil if the partition created by is a refinement of the partition created by A permil. The equality equivalence relation is the finest equivalence relation on any set, while the trivial relation that makes all pairs of elements related is the coarsest. The relation is finer than A permil on a collection of all equivalence relations on a fixed set is itself a partial order relation. Generating equivalence relations, given any set X, there is an equivalence relation over the set, ZAX, of all possible functions ZAX. Two such functions are deemed equivalent when their respective sets of fixed points have the same cardinality, corresponding to cycles of length 1 in a permutation. Functions equivalent in this manner form an equivalence class on ZAX, and these equivalence classes partition ZAX. An equivalence relation on X is the equivalence kernel of its surjective projection I euro X and X/. Conversely, any surjection between sets determines a partition on its domain, the set of primedges of singletons in the codomain. Thus an equivalence relation over X, a partition of X, and a projection whose domain is X, are three equivalent ways of specifying the same thing. The intersection of any collection of equivalence relations over X is also an equivalence relation. This yields a convenient way of generating an equivalence relation. Given any binary relation A on X, the equivalence relation generated by A is the smallest equivalence relation containing A concretely. A generates the equivalence relation A to be if and only if there exist elements x1, x2, xn in X such that A equals x1, B equals xn, and A or A, I equals 1. n1. Note that the equivalence relation generated in this manner can be trivial. For instance, the equivalence relation generated by any total order on X has exactly one equivalence class, X itself, because X to Y for all X and Y. Any subset of the identity relation on X has equivalence classes that are the singletons of X. Equivalence relations can construct new spaces by gluing things together. Let X be the unit Cartesian square, 0, 1, 0, 1, and let be the equivalence relation on X defined by a BA, 0, 1, a section. Then the quotient space X/ can be naturally identified with a torus. Take a square piece of paper, bend and glue together the upper and lower edge to form a cylinder, then bend the resulting cylinder so as to glue together its two open ends, resulting in a torus. Algebraic structure. Much of mathematics is grounded in the study of equivalences and order relations. Lattice theory captures the mathematical structure of order relations. Even though equivalence relations are as ubiquitous in mathematics as order relations, the algebraic structure of equivalences is not as well known as that of orders. The former structure draws primarily on group theory and, to a lesser extent, on the theory of lattices, categories, and groupoids. Group theory, just as order relations are grounded in ordered sets, sets closed under pairwise supremum and infimum, equivalence relations are grounded in partition sets, which are sets closed under bijections and preserve partition structure. Since all such bijections map an equivalence class onto itself, such bijections are also known as permutations. Hence permutation groups and the related notion of orbit shed light on the mathematical structure of equivalence relations. Let tilde denote an equivalence relation over some non-empty set A, called the universe or underlying set. Let G denote the set of bijective functions over A that preserve the partition structure of A, A-X A-G G X. Then the following three connected theorems hold, partitions A into equivalence classes. Given a partition of A, G is a transformation group under composition, whose orbits are the cells of the partition A. Given a transformation group G over A, there exists an equivalence relation over A, whose equivalence classes are the orbits of G. In sum, given an equivalence relation over A, there exists a transformation group G over A whose orbits are the equivalence classes of A under. This transformation group characterization of equivalence relations differs fundamentally from the way lattices characterize order relations. The arguments of the lattice theory operations meet and join are elements of some universe A. Meanwhile, the arguments of the transformation group operations composition and inverse are elements of a set of bijections, A. Moving to groups in general, let H be a subgroup of some group G. Let be an equivalence relation on G, such that A to be A. The equivalence classes of A also called the orbits of the action of H on G are the right cosets of H and G. Interchanging A and B yields the left cosets. A proof. Let function composition interpret group multiplication, and function inverse interpret group inverse. Then G is a group under composition, meaning that A-X A-G equals X, because G satisfies the following four conditions. G is closed under composition. The composition of any two elements of G exists, because the domain and codomain of any element of G is A. Moreover, the composition of bijections is bijective. Existence of identity function. The identity function, I(x) equals X, is an obvious element of G. Existence of inverse function. Every bijective function G has an inverse GA1, such that GA1 equals I. Composition associates. F, GH, equals H. This holds for all functions over all domains. Let f and g be any two elements of G. By virtue of the definition of G, f, x equals, f, x, and, f, x, equals, x, so that, G, f, x equals, x. Hence G is also a transformation group because function composition preserves the partitioning of A. Related thinking can be found in Rosen categories and groupoids. Let G be a set and let tilde denote an equivalence relation over G. Then we can form a groupoid representing this equivalence relation as follows. The objects are the elements of G, and for any two elements x and y of G, there exists a unique morphism from x to y if and only if x to y. The advantages of regarding an equivalence relation as a special case of a groupoid include, whereas the notion of free equivalence relation does not exist, that of a free groupoid on a directed graph does. Thus it is meaningful to speak of a presentation of an equivalence relation, that is, a presentation of the corresponding groupoid. Bundles of groups, group actions, sets, and equivalence relations can be regarded as special cases of the notion of groupoid, a point of view that suggests a number of analogies. In many contexts quotienting, and hence the appropriate equivalence relations often called congruences, are important. This leads to the notion of an internal groupoid in a category. Lattices, the possible equivalence relations on any set X, when ordered by set inclusion, form a complete lattice, called con-X by convention. The canonical map Ker, XX a con-X, relates the monoid XX of all functions on X and con-X Ker is surjective but not injective. Less formally, the equivalence relation Ker on X, takes each function f, zao x to its kernel Ker f. Likewise, Ker is an equivalence relation on XX. Equivalence relations and mathematical logic. Equivalence relations are a ready source of examples or counterexamples. For example, an equivalence relation with exactly two infinite equivalence classes is an easy example of a theory which is hypermale categorical, but not categorical for any larger cardinal number. An implication of model theory is that the properties defining a relation can be proved independent of each other if and only if, for each property, examples can be found of relations not satisfying the given property while satisfying all the other properties. Hence the three defining properties of equivalence relations can be proved mutually independent by the following three examples: reflexive and transitive, the relation a permale currency on N or any preorder; symmetric and transitive, the relation A on N, defined as arbor permale 0. Or any partial equivalence relation. Reflexive and symmetric, the relation A on Z, defined as arbor AAB is divisible by at least one of two or three. Or any dependency relation. Properties definable in first-order logic that an equivalence relation may or may not possess include, the number of equivalence classes is finite or infinite. The number of equivalence classes equals the natural number n. All equivalence classes have infinite cardinality. The number of elements in each equivalence class is the natural number n. Euclidean relations. Euclid's the elements includes the following common notion: 1, things which equal the same thing also equal one another. Nowadays, the property described by common notion 1 is called Euclidean. The following theorem connects Euclidean relations and equivalence relations. Theorem: if a relation is Euclidean and reflexive, it is also symmetric and transitive. Proof: arc a section BRC, an arb, AC, equals a arb, reflexive. Erased R section equals bra arb. Hence R is symmetric. Arc a section BRC, an arb, symmetry equals an arb. Hence R is transitive. Hence an equivalence relation is a relation that is Euclidean and reflexive. The elements mentions neither symmetry nor reflexivity, and Euclid probably would have deemed the reflexivity of equality too obvious to warrant explicit mention. See also, partition of a set, equivalence class, up to, conjugacy class, topological conjugacy. Notes, Garrett Birkhoff and Saunders MacLean, 1999. Algebra, 3rd ed. Pages 35, th 19. Chelsea. Wallace, DAR, 1998. Groups, Rings and Fields. Pages 31, th8. Springer-Verlag. Dummett, D.S., and Foote, R.M., 2004. Abstract Algebra, 3rd ed. Pages 3, Prop 2. John Wiley & Sons. Garrett Birkhoff and Saunders MacLean, 1999. Algebra, 3rd ed. Pages 33, th18. Chelsea. Rosen, pages 243-45. Less clear is A. Section 10.3 of Bas van Fraassen, 1989. Laws and Symmetry. Oxford University Press. Wallace, D.A.R., 1998. Groups, Rings and Fields. Springer-Verlag, 202, th6. Dummett, D.S., and Foote, R.M., 2004. Abstract Algebra, 3rd ed. John Wiley & Sons, 114, Prop 2. Bas van Fraassen, 1989. Laws and Symmetry. Oxford University Press, 246. Wallace, D.A.R., 1998. Groups, Rings and Fields. Springer-Verlag, 22, th6. Wallace, D.A.R., 1998. Groups, Rings and Fields. Springer-Verlag, 24, th7. Borsey, F. and Janelids, G., 2001. Galois Theories, Cambridge University Press, ISBN 0-521-80309-8, references, Brown, Ronald, 2006. Topology and Groupoids. Booksurge LLC. ISBN 1-4196-2722-8. Castellani, E., 2003, Symmetry and Equivalence in Bradding, Catherine, and E. Castellani, eds., Symmetries in Physics, Philosophical Reflections. Cambridge University Press, 422-433. Robert Dilworth and Crawley, Peter, 1973. Algebraic Theory of Lattices. Prentice Hall. CHPT 12 discusses how equivalence relations arise in lattice theory. Higgins, P.J., 1971. Categories and Groupoids. Van Nostrand. Downloadable since 2005 as a TAC reprint. John Randolph Lucas, 1973. A Treatise on Time and Space. London, Methuen. Section 31. Rosen, Joseph. Symmetry Rules, How Science and Nature Are Founded on Symmetry. Springer-Verlag. Mostly CHPTS. 9, 10. Raymond Wilder Introduction to the Foundations of Mathematics 2nd edition, Chapter 2-8, Axioms Defining Equivalence, pages 48-50, John Wiley & Sons. External links, Haswinkel, Michiel, ed., Equivalence Relation, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4, Bogomolny, A. Equivalence Relationship Cut the Knot. Access September 1, 2009, Equivalence Relation at Planet Math, Binary Matrices Representing Equivalence Relations at OEIS.